In this problem, we will find out how to solve a related rate problem. Related rates are when the derivative of one variable with respect to another variable, say time, is related in some fashion to another variable with respect to that same other variable, let's say time. The easiest way to look at this is to do some examples since each problem is in fact unique. So in this example, an 8-foot long ladder is leaned against a wall. The top of the ladder is sliding down the wall at the rate of 2 feet per second. Let L equal the length of the ladder in feet. Y represents the distance in feet from the top of the ladder to the ground. X represents the distance in feet from the bottom of the ladder to the wall. And T represents time in seconds. What I want to do is I want to choose all of the following that are correct descriptions of the relationship between the variables assigned above. Normally we'd write these on our own, but I want us to kind of see where they come from. So here we have a triangle, for example, for this example. We have Y on the vertical, X on the horizontal, and L down the hypotenuse. So one of the things we have is Y over X equals 64. And I don't see any relationship out of this that would give me Y over X is 64. So that one's not one that I would use. X plus Y equals 8 is also not one I would use. X plus Y certainly is not going to be 8. Now, X squared plus Y squared equals 64 is in fact a relationship I would see. So remember that the ladder is 8 feet long. The Pythagorean theorem tells me that one leg squared plus the other leg squared is equal to the hypotenuse squared. And so C is actually one of our relationships, and I want to go ahead and highlight that number. D is X squared plus Y squared equals 8. That one doesn't work because 8 isn't squared. We need all these sides to be squared to beat the Pythagorean theorem. E says L is equal to 8. Well, L is in fact equal to 8 because the ladder is in fact equal to 8. So we can say that E also is one that works. F says the derivative of L with respect to T equals 8. Well, that would be saying the length is changing, but the ladder's length isn't changing. So the derivative of length over time is not going to equal 8. G is the derivative of L over time is equal to 0. And that is true because the length is not changing. So its derivative should be 0. H is the derivative of L over T is equal to 2. And again, the length is not changing, so that can't be it. I is the X is equal to the square root of 64 minus Y squared. If you took C, the Pythagorean theorem, and solved for X, you would get the square root of X squared minus Y squared. So that one does in fact work. J is Y is equal to the square root of 64 minus X squared. If you took the Pythagorean theorem and solved for Y, you would also get the square root of 64 minus X squared. So that one also works. K says the derivative of X over T is 2. So now let's look again to see what's going on. It does tell us the top of the ladder is sliding down the wall at the rate of 2 feet per second. So 2 feet per second would be what it would be doing. And that's telling me what the top of the ladder is doing. So that's not what X is doing. X is the distance along. We don't know what that's equal to, so it can't be that one. dy dt equals 2. Again, that's could be what it is because the height is changing. But if it's sliding down the wall, then the distance on the wall is actually getting slower and lower. So that's going to be a negative number because it's decreasing. So it's not L. M is dx dt is equal to negative 2. Again, we don't know how X is actually changing because X is the distance along the floor, and we don't know what that one is. We know how fast it's sliding down the wall is 2 feet per second. So that has nothing to do with X. N is dy dt equals negative 2, and that is actually what's happening. The height is changing, and it's decreasing, so that's why it's negative. 0 is dl dt equal to -2, and again, the length is not changing. On the next page, we have dx dt equals 0, and again, we don't know how x is changing, so we can't pick that one. Q is dy dt equals 0. We already determined what dy dt is, so we can ignore that one. R is dy dt is equal to dy dx times dx dt, and this is kind of a rate of change. This is saying that y is changing over time. Y is also changing with respect to x, and x is changing over time. So R is actually one that makes sense to pick. Dx dt is dx dy times dy dt. Again, that also makes sense because we can talk about x is changing over time, x is also changing with respect to y, and y is changing over time. So we can actually pick S also. Dx dt, t says dx dt is equal to 1/2 64 minus y squared to the -1/2 times -2y dy dt. So if I look at this and I'm trying to figure out what y dy dt dy dx is equal to, I'm going to remind myself that we've already said that dy dt, that we already said that x is equal to the square root of 64 minus y squared. So I can take the derivative of x with respect to y using this formula here, using L. And when I do that, I would get 1/2 times the inside. So using the chain rule, you bring the power down, it's 1/2 times the inside to the -1/2 power, then times the derivative of the inside is equal to times dy dt, because we don't know how y is related to x, changes with time. So t actually works. Same reason u also works. Oh no, actually, I'm sorry, u does not work because it doesn't have the dy dt on the end. But v looks very much similar to t. It's exactly the same, except we did dy dt instead of the dx dt. W again doesn't work because it doesn't have the dx dt on the end. So we're going to use all these relationships we chose to help us answer the following question. What distance is the top of the ladder from the ground when the bottom of the ladder is 4 feet from the wall? Well, we want to know the distance the top of the ladder is from the ground, so we want to know what y is when the bottom of the ladder is 4 feet long from the wall. So we happen to know what x is equal to. X is equal to 4 feet. We want to find out what y is equal to. Well, going back to my relationships, I can see that I had a relationship that told me that y was equal to the square root of 64 minus x squared. So that's the relationship I'm going to use. Y is equal to the square root of 64 minus x squared. We know what x is equal to, so it's going to be 64 minus 4 squared. So we get the square root of 64 minus 4 squared is 48. So that's square root of 48 feet. Now the next question asks us, how fast is the bottom of the ladder moving along the ground at the point in time when the bottom of the ladder is 4 feet from the wall? Well, when I want to know how fast the bottom of the ladder is moving on the ground at a point, then I want to find dx dt. So I'm looking to find dx dt. And using letter t above, dx dt was equal to 1/2 64 minus y squared to the -1/2 times -2y dy dt. So that's the equation I'm going to be looking at. I've got dx dt is equal to -1/2 64 minus the square root of 48 squared times, well, actually, let's just write it out first so you can see where everything goes. So we have 1/2 64 minus y squared to the negative 1/2 times negative 2y dy dt. Using the y values we found above and letter n that says dy dt is equal to negative 2, once we can find dx dt. So we have 1/2 times 64 minus y squared, but y we found to be the square root of 48. So we have 48, square root of 48 squared. That's being raised to the negative 1/2 power times negative 2 times the square root of 48, because it's negative 2 times y. And that's going to be multiplied by dy dt, which again, we found to be negative 2. And all you need to do is simplify this and find out approximately what it's equal to. This simplifies and is approximately equal to 3.5 feet per second.